previous module, we were talking about molecular orbital theory of and we applied linear variation treatment to S2 plus molecule. We have started the linear combination of two atomic orbitals of hydrogen, and we have written the. I will skip through this slide just to recap what we did in the last module. So we wrote that this secular determinant, and from the secular determinant we calculated the energy values, two different energy values we calculated, E minus and E plus, and then corresponding to these two energy values we also calculated the eigen function psi a plus psi b, psi a minus psi b, and then we normalized this wave function psi a plus psi b and psi a minus psi b, and we found that the normalization constant is 1 over root under 2 into multiplied by 1 plus SAB within bracket, and then if you use another function, then you get the normalization constant 1 over 2 root under 1 divided by root 2 1 minus SAB. Okay, so these two normalization constant we got, and then this was the slide where I left you, and I said you that we have normalized eigen functions, we have the eigen values, and we this tells you that when you go for a linear combination, your psi trial or psi MO is linearly combined by Ca psi A plus Cb psi B. Okay, then what you get is that plus minus psi B. Then this way I have written as Ca and Cb also value we found, and I said you that Ca plus minus psi B are the two functions. Okay, so if you square the function, you get the probability density. So if you square individual psi A square and psi B square and individual atoms probability, you sum it up, you get this one. But if you square this function psi A plus psi B and psi A minus psi B, what you get? You get an additional factor of 2 psi A plus psi A psi B, and this additional factor is the additional electron density in one case where the psi A plus psi B, and in another case in psi A minus psi B, this additional factor decreases the electron density because it becomes minus 2 psi A psi B. Okay, so in one of the molecular orbital, the electron density decreases, you see, in the internuclear space, and in another case the electron density increases in the internuclear space. The figure should be like this one. Okay, so in the internuclear space, when it's an atom, you do not have an electron density here in the internuclear space, but when it gets bonded when it is in the form of molecule, the electron density increases. This was the point where I left you. Now, since we have the energy value given HA plus HAB, SA plus SAB, HA minus HAB, SA minus SAB, so what we need to know is that what is the difference between the two energy levels. One thing. Another thing which we need to know is that these are HA, HAB are integrals. So how to find out the value of the integral? These two things we will be doing today. Okay, so if we look at the calculation of difference of energy between energy levels, then it's very simple. What you can do is delta is E plus minus E minus, and you have the value of E plus and E minus, so put the E plus E minus value, HA plus HAB divided by SA plus SAB minus HA plus HAB minus SA divided by SA minus SAB, and then you divide it, and when you divide it, what do you get? In the denominator you have SA plus SAB multiplied by SA minus SAB, and in the numerator you have HA plus HAB multiplied by SA minus SAB minus HA minus HAB and SA plus SAB. And if you expand the terms, what you find is that these two terms HA SA and HAB SAB you can omit, and then you have the term HA SA, and so this will be positive term, this will be positive term, these two positive and negative will go, and here you have HAB, SAB negative term, and minus multiplied by minus will make this positive, so these two terms will go. It's colored like to facilitate the things for you. Okay, so these two terms will go, and whatever you have here is will be SA square minus SAB square, SA square minus SAB square, and SA into SAB and SA into SAB plus and minus, so this will also go. Okay, so what you have in the numerator is HAB minus HA plus HAB this one minus minus plus and minus HA divided by SA square minus SAB square. Okay, and when you take this, look at this one, HAB so 2 HAB and you have minus HA SAB 2 HA 2 HA okay. So 2 multiplied by HAB minus HA divided by SA square plus SAB square. So this is what is the delta A value which we obtain when we subtract E minus from E plus. Okay. And for H2 plus molecule, what we know is that SA is equal to 1, obviously, SBB is equal to 1 because this is the normalization condition, and I have written psi 1 SA means first psi 1 SA is the wave function of 1s atomic orbital of hydrogen atom, which is an orthonormal function, which is already normalized. So the value is 1. Here also the value is 1. And if you write SAB as S, then what you can write? Your delta E will be HAB SA minus HA SAB. You see, HAB SA minus HA SAB. So nothing to do with this one. Numerator remains same. SA square minus SAB square. So what is it? How does it changes? The SA square becomes 1 and SAB square becomes S square. Just SAB we have written as psi 1 SA psi 1 B as S. So write it S square. Okay, and this SAB again becomes S. Okay. Now what we say is that this is the overlap integral. This S is I am writing Taman again so that while you watch the video, you remember that what are these integrals. HA is Coulomb integral. And HAB is exchange integral or resonance integral. Or when you write H, Hamiltonian is there. When you write S, Hamiltonian is not there. These are the easy way to keep it in your mind. Okay. So what we say that this overlap integral value is very low. It's between 0.2 and 0.24. So if the overlap integral itself is 0.2 and 0.24, then S square will be even lower. So now we assume that S square becomes equal to 0, almost approximately 0. We just approximate it, and it's all approximation because we are doing variation treatment, so it's all approximation. So approximately this S square becomes equal to 0, and so HAS and into S will also be 0 because HAS, again you are multiplying HA with S. So S is a very small value, so we suppose HAS also a small value. So assume S square to be 0 and assume HA into S also is 0. Then what do you get? The difference between the two energy levels is 2 HAB, and this HAB we give a symbol 2 beta, where beta is HAB and HAB is what? HAB is exchange integral or resonance integral. Since it is H, so Hamiltonian will be there in between the two wave functions. So psi 1 SA is the function, Hamiltonian is there, then again the function is there. Okay. So this HAB we give a symbol beta, and the difference between the two energy level is 2 beta. What does it mean? That if you have two energy levels, one is bonding molecular orbital and another is anti-bonding molecular orbital, then the difference in the energy delta E is equal to 2 beta. So what we can say is that if these are the 1 SA and 1 SB energy, then the difference between this energy and the bonding energy is beta, and then again this energy is also beta. So the difference between sigma 1s and sigma 1s star orbital energy is 2 beta, and this is what you draw as an energy diagram, and you say it's a molecular orbital diagram. Okay. So we calculated the difference between the energy of bonding and anti-bonding molecular orbital equal to 2 beta. Of course, we have assumed made assumptions, many assumptions, but more or less we got the equidistant from the atomic orbital energy. One goes down the energy and one goes above the energy of the atoms, but it remains, it is equidistant from the same. Of course, if you don't assume this, then the value will be different, but if we make these assumptions, we get energy equal to delta is equal to 2 beta. Okay. So this is what is the difference in energy. Now the question is that, okay, fine, we have this energy levels, bonding and anti-bonding energy is known to us. So now here we see SA instead of SA we have written 1, SA instead of SA we have written 1. Now if you want to know the calculation of the actual energy, then what you need to know, what you need to calculate is the value of these integrals HA, HAB and SAB. These integrals must be calculated in order to get the actual energy of the bonding molecular orbital and anti-bonding molecular orbital. Okay. This is also the energy, but this is in terms of the your integrals. Okay. So what we can do is we will try to explore that how to calculate the molecular energy levels and how to calculate these integrals. And again, when you have to calculate the integral, you have HAB, which includes the Hamiltonian. So again, we go back to the Hamiltonian, the same thing. Okay. Now, this is the most simplified form of Hamiltonian which I have written here. Otherwise, what the Hamiltonian includes, you know, if I write Hamiltonian includes kinetic energy term and plus potential energy term. The kinetic energy term is minus h cross square divided by 2m del square, and then potential energy depends upon the interaction which is taking place. So this part of the energy minus E square by Ra minus E square by Rb plus E square by R is the potential energy term with many simplifications, because 1 by 4 pi epsilon naught permittivity constant is omitted here. We have supposed that the energy, the charges present on the nucleus and the electron is same, the value is E. Okay. So these assumptions are there, but it's very simplified version I have written because it is easier for you to understand this way. Then in this particular thing, what I have written is kinetic energy term is the only minus h cross square divided by 2m del square. So actually, it should not be like that, because you have three different particles: HA nucleus, HB nucleus, HA nucleus, HB nucleus, and electron. So ideally, the term for the kinetic energy should be, if I write minus h cross square divided by 2m del, then I write HA square minus h cross square divided by 2m del HB square. These are for the two nucleus. Then minus h cross square divided by 2m del E square. Then you have potential energy term. So potential energy term should be both attractive term and repulsive term. So we write the attractive term first, minus 1 over 4 pi epsilon naught E square by Ra, then minus 1 by 4 pi epsilon naught E square by Rb, then plus 1 over 4 pi epsilon naught E square by R. With this term, we have assumed that the charge present on the electron and charge present on the nucleus is same and is equal to E. Okay. Now, these two terms, which is the term for the nucleus is omitted because of Born-Oppenheimer's approximation. I said you earlier also. It's a very important approximation. Born-Oppenheimer's approximation. And we suppose electron to be moving in the field of frozen nucleus. Nucleus is static. So the kinetic energy term is omitted, and now you have only one term of the kinetic energy, and the rest of the terms are for potential energy. So this is the term for the kinetic energy, this is the term for the potential energy. Okay. So if we use this and this is the most simplified version of the Hamiltonian which I could have written here. Okay. And why I have written it, I explained it because we can explain it. Now, so if you have to calculate the value of HA, you need psi 1 SA, then H is the Hamiltonian, psi 1 SA d tau. So put the value of Hamiltonian in this integral. HA is equal to psi 1 SA minus h cross square divided by 2m del square minus E square by RA minus E square by RB plus E square by R 1 SA d tau. Okay. Now, once we have put the value of Hamiltonian in the integral, then we can separate the terms into different integrals. So what I have done is that I have written integral of psi 1 SA minus h cross square divided by 2m del square minus E square by RA. Now you see, what does this 1 SA d tau? So what does this first term tells you? This first term, in this first term, the Hamiltonian which I have used, H which I have used is minus h cross square divided by 2m divided by 2m del square minus E square by R. So can you think of what does this indicate? Which system does it indicate? It indicates a hydrogen atom, because if you have a hydrogen atom, then you have an electron and you have a nucleus. You have a nucleus and you have an electron. Okay. So the potential, the Hamiltonian for this is potential energy is minus E square by R, and the kinetic energy is minus h cross square divided by 2m del square. So this Hamiltonian is the Hamiltonian for hydrogen atom system. Okay. And better to write not m, let me write 2 mu. Okay. Minus h cross square divided by 2 mu del square minus E square by R. Okay. So this indicates the Hamiltonian of hydrogen atom. Oh, I have written here eigenvalue equation for hydrogen atom is this one. So this is your Hamiltonian of hydrogen atom, and the eigenvalue equation is what? H psi 1 SA is equal to E psi 1 SA. This will be the eigenvalue equation. So what you can write is, this is your eigenvalue equation. Okay, and in the rest of the term, what we have done, psi 1 SA is in its place, then minus E square by RB psi 1 SA d tau plus psi 1 SA plus E square by R 1 SA d tau. Okay, so we have this integral, we have this integral, and we have this integral. In this integral, this part minus Hamiltonian psi 1 SA could be written as EH1 SA, because eigenvalue equation is this one. Okay, so if you put this value in this equation, what do you get? HA becomes equal to psi 1 SA, then rest of the part becomes EH1 SA, psi 1 SA, because of the eigenvalue equation of hydrogen atom. So EH1 psi 1 SA d tau plus, again you have minus E square by RB, so you can bring it outside the integral, and then integral of psi 1 SA d tau, and then plus term you have, and this E square by R you can bring outside, and psi 1 SA d tau. Okay, so this we can do. Finally, This EH you can bring again outside. So EH is outside, then psi 1 SA d tau minus E square by RB psi 1 SA d tau plus E square by R psi 1 SA d tau, integral of psi 1 SA d tau. And you know that integral of psi 1 SA d tau is equal to 1. So whatever HAA you get is EH plus minus E square by RB plus E square by R. Okay. Now, what can I write this equation? This equation I can write as HA is equal to EH. Then I write minus J, because this will be minus term, minus J and plus E square by R, where this J term is actually this one, this integral. Okay. Actually J term is this integral. So we can write it like this one. And if it is there, if this term is there, then it will not be equal to 1. If psi 1 SA d tau I have written, then it's equal to 1. Okay. So this is the HAA value. HAA value. And exactly in the same fashion, you can go and find out HAB value. So HAB value is psi 1 SA H psi 1 S B d tau, and so you put those terms. Again, this is your you find out the hydrogen atom Hamiltonian, and then again you write minus E square by RB and then plus E square by R, and again you use the eigenvalue equation of the hydrogen atom, and what you get is HAB is equal to integral psi 1 SA EH 1 psi 1 S B d tau plus minus E square by RB psi 1 SA psi 1 S B d tau plus E square by R integral of psi 1 SA psi 1 S B d tau. Now you see, what we can write is HAB EH into S, we can write psi 1 SA psi 1 S B d tau. See the difference between the two. Here we have EH multiplied by integral of psi 1 SA psi 1 SB d tau, which became equal to 1. No, sorry, no, so it was both psi 1 SA psi 1 SA d tau. Okay. So it was equal to 1, the normalization equation. Okay. Okay, normalization conditions, psi 1 SA d tau is equal to 1. So you do not have an S here, but in this case, when finding out the HAB value, you have psi 1 SA psi 1 SB d tau. Okay, so that 1 SA integral of psi 1 SA psi 1 SB d tau is actually SAB, which I have written as S, overlap integral. So along with EH, you have S value also. Then again you have minus K. So minus K is psi 1 SA minus E square by RB psi 1 SB d tau. Okay. So minus K, and plus again with E square by R, you will have psi 1 SA psi 1 SB d tau, which is equal to S. So you have this S, you have this S, and instead of J, you have K here. Okay. So the different, what is the value of J? What is the value of K? These are integrals, J and K integrals. Okay. So if you put these values into the original equation of E plus and E minus, what you get is EH plus becomes equal to EH minus J plus E square by R, plus HAB is EHS minus K plus E square by R into S divided by 1 plus S. So you can write EH, this EH and this EHS, you can write EH 1 plus S minus J and plus K will be, you can write, because this is minus J minus K, so minus within bracket you can write J plus K, plus E square by R you can take common from this one and from this one, and it will be again 1 plus S. Okay. So what does it mean? You have 1 plus S here also, you have 1 plus S here also, but you don't have 1 plus S here. So what you can write is EH minus J plus K 1 plus S plus E square by R. Okay. So the value of this energy depends on the energy of hydrogen atom, R value, that is internuclear separation, overlap integral, and the two integral J and K. And J and K integral is what? J integral is psi 1 SA minus E square by RB psi 1 SA d tau. K integral is psi 1 SA minus E square by RB psi 1 S B d tau. It's a very small difference. The two different wave functions, same wave functions. Okay. So this will give you the value of E plus. In the same fashion, one can go and find out the value of E minus. And E minus value we obtain is EH minus J minus K 1 minus S. You see the difference. Here you have EH minus J plus K 1 plus K plus E square by R, and here you have EH minus J minus K 1 minus S plus E square by R. This is the only difference at this point. Okay. So E plus and E minus value depends on the value of integral J, integral K, S value as well as R. Internuclear separation. Okay. And this is, if you go and find out these values, now if for finding out these integrals, what you do? You have the integral, but you need to know what is the psi 1 SA, what is the psi 1 SB, and then only you can integrate. So if you write the psi 1s, both 1s A or 1s B or 1s atomic orbital of hydrogen atom, psi 100, psi 100, and which is 1 by root pi 1 over A naught raised to the power 3 by 2. So at a constant, I am writing for your convenience always a constant multiplied by exponential minus R divided by A naught. Okay. This is the integral. Okay. So if you use the calculated value of these integrals, okay, calculated value of these integrals, taking A naught is equal to 1 atomic unit, comes out to be J is equal to this one, K is equal to this one, and S is equal. Knowingly, I did not go into the details of calculation of these. One can find somewhere. But look at this one. The value of J we have calculated in terms of internuclear distance. The value of K I have calculated in terms of internuclear distance. And the value of S also I have calculated in terms of internuclear distance. So all the integrals of this equation, E plus and E minus, is E plus and E minus. Wait. This will be E minus. Make a correction. This will be E minus. Make a correction. Okay. So this E plus and E minus is known to you, all values in terms of internuclear separation. So what we can do is we can find out the energy of E plus and E minus with respect to different R values, because J is known in terms of internuclear separation, K is known in terms of internuclear separation, and S is also known in terms of internuclear separation. Then what you can do is, okay, so what you can do is that J is known, K is known, S is known, and you can find out the energy for these integrals. So these integrals are positive and decreases towards 0 at large internuclear separation. S and K decreases to 0. S and K decreases to 0 on account of exponential terms, and J on account of 1 by R. Okay. So if you look at these integrals, I've explained that how these integrals will vary with respect to internuclear separation. So S and K decreases to 0 on account of exponential terms, and J on account of 1 by R. S and K. So S and K, you have exponential terms. This has exponential terms. So it will decrease because of these exponential terms, and J will decrease because of 1 by R. Okay. So it will decrease to 0 at certain R values. S and K decreases to 0 on account of exponential and J on account of 1 by R. The integral J measures the interaction between the nucleus and the electron density centered on other nucleus, and the integral K is a measure of interaction between a nucleus and the excess electron density in the internuclear region. So, you see what is J? J is this integral 1SA 1SA, and K is 1SA 1SB. So, here we are talking about the electron density in between the nucleus. Here we are talking about electron density of one electron nucleus, electron density around one nucleus and the other nucleus. So, it's written here. The integral K is a measure of interaction between a nucleus and the excess electron density in the internuclear distance, and the integral J measures the interaction between the nucleus and the electron density centered on other nucleus. Okay. So, these are different measures, and when we actually calculate these energy values, we get energy like this one for E plus and E minus. This I have taken from a book, Quantum Chemistry by R.K. Prasad. So, the reference also I have given you. And if you look at the E plus value, it goes on decreasing, becomes negative 0.65, and at this point, from this points onward, it again increases minus 0.059, minus 0.048, minus 0.038, and again it increases. Okay. But it remains in the negative region. But if you look at the E minus value, it also decreases to 2.35, 1.019, and again, but it remains positive. So, if you plot E plus and E minus, you get a graph like this one. You have a minima at 2.5, okay, as per this data, you have a minima at 2.5. This internuclear distance R is the distance for bonding, okay, or we can say chemical bond. This graph is we are very familiar with this graph. Okay. So, you have an energy decrease in one case, and you have energy which remains positive in one case. This is your bonding molecular orbital energy, bonding MO energy. This is your anti-bonding MO energy. So, anti-bonding energy remains always positive, but the bonding molecular orbital energy has a energy minima which is at the distance of bond length. Okay. So, this is the simplest picture possible for the hydrogen H2 plus molecule ion which we talked about. An extension of this will be talking about H2 molecule and talking about other higher molecules. Okay. We will see how do we apply variation treatment to other cases in the next module. Okay. And then remember that approximation methods I said you, there are two different approximation methods. One is variation, another is perturbation. So, after finishing variation treatments application, we will go for perturbation treatment also. Thank you.